Okay, let's go ahead and look at section 4.4, evaluating logarithms and the change of base theorem. So there's two really common logarithms that we use. The first one was the logarithm developed by Napier. I mentioned him in the last section. He has a very interesting life. I've got Google here. It's actually just Google, just plain old Google. Why am I'm Googling Google. Can you believe that? Napier logarithms. See what we get. John Napier. So he has a really interesting life. I just brought up his name so you could see it. You can read about him on his own, advances in mathematics. He was generally credited with coming up with logarithms. So, but he had a lot of other interesting views on theology and the occult and all kinds of other things. So if you're interested, you can look at that on your own. So let's get back to here. So what we have is some notation. Before you heard me complaining about it, we were given the notion log to the base b of x. And I was just always complaining because at every turn they were changing the base around. But now we're actually just looking at log. Log with any base written. When the base is left blank, it's not written, then we assume that the base is base 10. So basically, log of x is the same as the base 10 log. So let's just take a look at this. I actually pose an interesting question here. So if no base is indicated in a subscript, we assume the base is 10. That's also the same with your calculator keys. And it's not an arbitrary choice, although it may have resulted by chance, I don't know. It's the fact that we have 10 fingers. I guess if the Maya had survived and not been conquered, etc., they actually had a base 20 system. They counted on their fingers and their toes, and the base 10 logarithm may have been more natural. So here's the question I pose. This coincidence of nature makes one wonder if there's a more natural, in some sense of that word, base other than 10, and we'll actually find out the answer to that is yes. So here, rejoice. You get to use a calculator with the log key to find the values of log 1000, log 142, and the log of 0.005832. All good and well except that first one. We can actually figure out the answer to A without using a calculator. Remember, log of 1000 is the same as log to the base 10 of 1000. So if log of 1000 is equal to x, recalling that the unwritten base is 10, that implies 10 to the x is equal to 1000. And as soon as we write 1000 is 10 to the third, then we can use our properties of solving for exponential equations to declare that x is equal to 3. And we'll actually find that. Again, I use Linux, the Ubuntu distribution. So the calculator I have here is not the calculator you have. If you're using Windows, there's a little pull-down menu somewhere up there. It goes from basic mode. This has a basic mode too. But they don't call for the Windows calculator. It's called scientific mode. Feel free to pull that up, or if you have another calculator. So let's actually use the calculator. Here is my log key. So I'm going to put in log and then 1000. And when I hit equals, it will give me 3. Doing the same thing for the log of 142. Makes math a lot easier when you have computer's help, right? 142. And let's think about this for just a second, because I don't expect you to know the answer, but this is just putting them up in there. I mean, just entering in the number in a calculator is way too easy. It implies no math whatsoever. So we know that the log of x is an increasing function. So what does that mean? A function, this is a good time to review this, a function is said to be increasing over an open interval a, b, there's our open interval, if whenever x1 and x2 are in the interval AB with x1 less than x2, we have f of x1 is less than f of x2. So graphically what that means is, if here's my open interval A and B, then any function that's increasing can never be constant. It doesn't matter what it is outside of A or B, because it's increasing over the open interval. But it can be really increasing, not so increasing, increasing more, not so increasing. As long as it's going up and it never goes flat, then it's increasing. So why am I talking about that in connection to 1b? Well, because it's increasing, it's increasing over the entire real line, I know that 100 is less than 200. So log of 100 is going to be less than log of 142, which is less than log of 200. So I know what the log of 100 is. The log of 100 is 2. So the value I'm looking here is going to be greater than 2 and less than the log of 200, and I will give you that value right now because I computed it. Suppose we knew its value. That value turns out to be 2. That's fine. That value turns out to be 2.31. And indeed, when we look at this in the calculator, when we find the log of 142, oh, sorry, is there a backwards? I just clear it and do it again. Log of 142. And we're going to find it's going to be greater than 2, but less than 2.3. And indeed, it's equal to 2.15. And it goes on. So there's that. So now let's find the log of, so this is 1c, the log of 0.005832. Now right now we don't quite have the tools to estimate this, but later on when we look at the graph we will. So we'll just enter it in the calculator, because this is a calculator exercise. So this is log, meaning log to the base 10 of 0.125832, and we get an answer. And the important thing here is that you notice that our answer is minus 2.234182485. It's probably an irrational number, and it continues on and on and on. But either way it goes, that's close enough for us. So now let's look at some applications. So a lot of the scales that are useful to us in science, including the scale for the spread of COVID-19, if you've actually ever looked at that. And let's actually take a look at it right now. I actually have a COVID-19 folder. Yeah. So here we actually have, it's kind of nice, this 1.35 daily % increase. And we're getting further and further away. But if you notice this scale, this is, if you want the update, just Google 91/DIVOC COVID-19 blah blah, you'll get it. Those are good enough Google words. But you'll notice that the scale down here, that doesn't look like exponential functions to me. That's because our scale is log. So notice that the x values are our regular x values, but our log is applied to the y. So instead of, we have 500, 1,000, the space between 1,000 and 10,000 is the same distance as the space between 10,000 and 100,000, which is the same thing as the same distance as the space between 100,000 and up there would be 1 million. If we want to look at it at the regular Cartesian coordinate plane, I can hit the linear scale, and you can see the linear scale of the 1.35 daily increase. And you can see that we are not, it looks like we may actually be flattening out right there, and that's a good thing. So anyway, let's get back to our problem. So the point, the reason I went off on that little tangent, is there's an awful lot of things in science that we measure logarithmically because they either increase or they decrease exponentially or logarithmically. So the Richter scale, for example, for earthquakes, a earthquake on the Richter scale of 6 and 7, that's a huge order of magnitude. Even though it's just 1 point up on the scale, a Richter scale 7 earthquake versus a 6 one is much more serious, much more powerful. So in this particular example, it's chemistry. It's the one area I'm really weak in, although I did like chemistry in high school, especially playing with the chemicals when the instructor was gone. But at any rate, the scale that measures the pH, which is a measure of acidity of a solution, is given by pH. Remember, that's just saying some measurement of acidity is minus log H3O plus, where H3O plus is the hydronium ion concentration in moles per liter. So if your chemistry majors out there, all of this is familiar with you. The plus tells you it's an ion. It's missing an electron, I believe. 3 parts hydrogen, 1 part oxygen. So it's clearly not H2O. It's not water. And the concentration of moles per liter will also be familiar to you. So what we want to do is we want to find the pH of a solution of H3O plus, the hydronium ion, that equals 2.5 times 10 to the minus 4. So here how we're going to do this one, and we're going to do it we're going to use the calculator, but not the calculator for all of it, just part of it. So we're going to do 2a and 2b. Again, the calculator will be used, but not in the way you might be thinking. So this is example 2a. So we just start with the formula, and I just got rid of the formula. So we start with a formula that says if you want to write acidity there, but that's all that means. It's a measure of acidity. And I just uploaded a corrected version of this formula to the web. So if you download this worksheet after tonight, any small typos have been corrected. In the original one, I forgot to put in the minus. So what we're doing is we're calculating minus, this is the base 10 log of, see now what we're doing, 2.5 times 10 to the minus 4. So we're literally going to use properties of logarithm. So this is the property of 2.5. Remember that the log of a times b is equal to log a plus log b. And that's how we're going to calculate this one. So this is going to be minus the base 10 log of 2.5 plus the base 10 log of 10 to the minus 4, which is equal to minus the base 10 log of 2.5, and now I'm going to use log of some b to the nth power at any base is equal to b is equal to n times log b. This is the property I'm using. So this is equal to minus 4 times log 10. So now let's get out our calculator. The log of 2.5 is equal to, we'll just do 0.4. That's close enough. 0.4 minus 4. Do we need the calculator to evaluate log to the base 10 of 10? Log to the base 10 of 10 is equal to some number x. That's what we want to solve. But this implies 10 to the x is equal to 10. So x is equal to 1. So this is 4 times 1. And we have minus 0.4 minus 4 is minus 3.6. And all of that is, I'm taking the double negative here. So the answer is the pH is about 3.6. So literally, we only use the calculator to find one value, the log of 2.5, the log to the base 10 of 2.5, because the formula itself is given using the base 10 log. So the next thing we want to do is example 2, is we want to find the hydronium ion concentration of a solution with pH 7.1. So again, we have the formula pH is equal to minus log to the H3o hydronium ion. So what we want to do, so notice this is a quantity here. It's a concentration in moles per liter. That's the unit. So whatever we find is going to be in moles of unit. So our pH is given to be 7.1. And that's minus log to the base 10 of some quantity x that I seek. So this is the same, if you need it written this way, as minus log to the base 10 of x is equal to 7.1. So let's multiply both sides through by a minus. So that gives me log. And here I just wrote the base 10 there just to remind you of x is equal to minus 7.1. So what is x equal to? X is equal to 10 raised to the minus 7.1 power. So which, if you remember your exponents, is 1 over 10 raised to the 7.1. And that turns out to be about, you can use your calculator there to find that out. How would you find that out? I hesitate because I'm using a calculator that I'm sure you all don't have. And some calculators should have x to the minus 1, which is the same as 1 over x. So what you would do is you would find, this is how I'm going to do it. It's like teaching you how to do calculators. So here I have x to the y. So I'm going to do 10 as my base, x to the y, and then I'm going to enter in 7.1. It equals. And now I'm going to find that if you have a 1 over x, which is the same as x to the minus 1, you hit that key, and there you get the answer. And I'm going to write that as 0 point, and then there's 7 zeros. 7, 9, but I'm going to move my decimal over 8 places and write this as 7.9 times 10 to the minus 8. Much more concise and much more manageable than looking at all of those zeros. So our next example is decibel noise. You know that noises that are really loud are measured in the decibel scale. Well, now you can figure. Now we've got the formula for it. So the loudness of sound is measured in decibels. The measurement depends on the context of an original sound intensity, symbolized by I naught. When you see the subscript down here that's a 0, we usually say naught. It's the English. The English, many times, so I'm just going to spell it out for you. So you may not be able to understand what I'm saying exactly. Now, some people will say I sub 0, but others will say I naught. N-A-U-G-H-T. I think that is the spelling. That's what it sounds like. I naught, like is you ought not do that. So, at any rate, the measurement depends on the context of an original sound intensity, symbolized by I naught, which corresponds to a very faint threshold of sound audible to humans. So they want to find the smallest sound that humans can hear, and that actually varies according to your age, what sounds you can hear and what is audible. Of course, children being the best at all of it, and elderly people being the worst. If a particular sound is measured to have intensity I, then the decibel rating of the sound is given by the following formula. D is the decibel rating, 10 times log of I divided by I naught. So we're going to find the decibel rating of a sound with intensity 10,000 I naught. So it sounds like this seems like it would be a difficult problem. We don't even need a calculator. So really we're just exploring uses of logarithm properties. So this is example 4. So we have D is equal to 10 log I over I naught. And we're given that I is equal to 10,000 I naught. So we just now figure it out. D is equal to 10 times log of 10,000 I naught divided by I naught, which is equal to 10 times the base 10 log. The I naughts cancel, so that's kind of nice. So it's 10 times the log of 10,000. And you should have no problem at this point in realizing that the base 10 log of 10,000, you just count the zeros. Since it's base 10, this is 1, 2, 3, 4. So it's 4. So the decimal level or reading is 40. So not near as bad as you may have been thinking. Did not even need a calculator. So now let's just go into here. So this is the more natural logarithm that I was talking about earlier. Instead of the base 10 logarithm, we have this logarithm. So when we were looking at the interest compounded daily, we encountered what is known as Euler's constant E, which the book stated was the result of continuous compounding of interest. And in mathematical terms, E is the result of what is known as taking the limit of a function as the value of x approaches infinity. In particular, we note that E is equal to the limit as x goes to infinity of the expression 1 plus 1 divided by x raised to x. In other words, E is the horizontal asymptote obtained by the following function. F of x is equal to x plus 1 divided by x raised to the x. So you should be able to figure out that x plus 1 divided by x is the same as 1 plus 1 over x. So that's what I say right here. And notice that this equation here, equation 2, is an exponential like function. it's exponential like because the base itself, which is what's here in parentheses, varies as the exponent x changes also. So it's exponential like, and that's the reason it has a horizontal asymptote that's equal to e rather than 0. And here, if we actually enlarge this picture, I plotted it on the domain of the real numbers. F of x is a real valued function, and you can see that the value of e is 2.1 something, and it quickly approaches on both sides. The value of y is equal to 2 point whatever that is. Down here it approaches it a little bit more slowly, it looks like, than on the right hand side. And all we care about is for the domain of positive numbers anyway. So here we have another basically symbolic notation. So if Euler's constant E is used as a base, now notice this is an irrational base. It's actually even more than irrational. E is called a transcendental number. And if you take calculus, you may get some indication of what that means. I doubt it, though. I actually didn't learn that until we took abstract algebra. That was in second semester. At any rate, we denote by this symbol, ln x is equal to the log to the base e of x. And that's also a key found in your calculator. Right there is the base 10 logarithm. Right there is the natural logarithm. And for most mathematicians, this is the only logarithm that we ever use. Not so for scientists, but mathematicians almost always use the natural log. As a matter of fact, we use it so constantly, we've even changed the default symbol, and we will use log, which normally for scientists means log to the base 10. We will literally use that to mean the natural log. So this is far from universal amongst STEM majors and scientists. But it's how we use this, and this is certainly the, if you use ln of x, then there's no ambiguity. Here you mean log to the base e, where e is Euler's e. So we are lazy, and we say ln of x for this right here. Or sometimes we'll say the natural log of x. I'll almost always be lazy and say ln of x. And this is the graph of the natural log of x. So notice right here that it crosses the x-axis. So y is equal to 0 when x is equal to the value of e. So it's just, e is just a little bit greater than 2. And for this particular case, let me bring this up here, move this around. We can note, we already know that if f of x is equal to ln of x, where the domain is 0 to infinity, then by what we're seeing right here, if x is greater than 0 but less than e, ln of x is itself greater than or equal to, sorry, I wrote the exact wrong direction here. If x is between 0 and e, over in this part right here, then ln of x is less than 0. Just some things to keep in mind. So we're not going to use a calculator to find this first one. Looking at example 5, we're going to use our mathematical knowledge. So we want to find the natural log of e cubed. So we want to know what the value of x is. But remember, this is to the base e. We don't write it. So if ln of e cubed is equal to x, that implies e to the x is equal to this number, e cubed. So x is equal to 3. And there's absolutely no reason to use the calculator. But if you want to experiment around with the calculator, you have to find your constant e. Right here it says it's Euler's number. And now we're going to take the natural log of e raised to the third power, and it's going to give us 1. That's not right. It's 3. I don't know what I did there. It's certainly not 1. The answer is 3. Maybe I'm supposed to put that in parentheses. Or maybe this calculator is literally wrong. But now I'm actually curious. Is this a... You never can tell with Ubuntu who actually did this calculator. Let's actually do a clear and do ln of e raised to the third power. And do it that way. There we go. So it was just one of those I needed parentheses types of things. You never can tell. Calculators can be our friends and our enemies. So back to here. The next one, we're going to find the natural log of 142. You literally just bring up your calculator, hit clear, enter in natural log 142, and hit equals, and that's your number. And we already knew that it was going to be positive, right? And for number C, we know our number is going to be negative because this number right here is greater than 0 but less than the value of e, which is 2 point something. So when we enter into the calculator, the natural log of 0.005832, we're probably going to see a decent, for logarithm, maybe a -2 or a -3 answer. Oh, it's even more than that. It's -5. So again, not that difficult of questions. And this one isn't so bad either. So literally none of these are difficult. The last page, I actually am going to give you a computational exercise. I will either upload a extra credit or a homework, or it will be part of your Canvas exam. But that's the next page. This is really easy, this particular example. So carbon dioxide in the atmosphere traps heat from the sun, a major cause of global warming. The additional solar radiation trapped by carbon dioxide is called radiative forcing, and that's the difference between sunlight energy absorbed by the Earth and energy radiated back to space. It's measured in watts per square meter, signified by W over meter squared. If you're in STEM and doing physics or engineering, all of these units are very important. In 1896, the Swedish scientist, no idea how to say it, Svante Arrhenius, no idea, modeled radiative forcing R, caused by additional atmospheric carbon dioxide using the logarithmic equation. R is equal to K times the natural log of C divided by C naught, where C naught is the pre-industrial amount of carbon dioxide. We can find C naught quite accurately by looking at ice core samples. They have little air bubbles that have been trapped in ice for many thousands of years, and we can carefully extract that air and analyze it and know how much carbon dioxide is in there. C is the current carbon dioxide level, and K is a constant. Arrhenius determined by experimental measures that K was between 10 and 16 whenever C was twice the value of C naught. So just to explain what's going on here, Arrhenius was able to establish a lower and an upper bound on the constant K. And sometimes that's really important. This is not an exact value of K, and the exact value of K has to be determined experimentally, but at the time it allowed one to give range estimates of radiative forcing. So basically the best and worst case scenarios. So all of that introduction, all we're going to need right here is this formula. So we're asked to let C be 2C naught. Is the relationship between R and K linear or logarithmic? So you just saw the different scales right there. So let's do it. So the first thing I'm going to need, this is example. For those of you who like to fast forward when I go and get off track, I like to do this so you can see, if you're looking on the fast forward, that I'm getting ready to do example, my gosh, this is example 7, 7a. So we need the relationship. R is radiative forcing, K is some constant. We have the natural log of C divided by C naught. So we're given that C is equal to 2 C naught. And we're asked the question, is R linear? So we can treat R as the y-axis. So in other words, I'm saying let R equal y in your mind. So let's go ahead and work this out. So R is equal to some constant K times the ln of 2 C naught divided by C naught. So R is equal to some constant K times the ln of 2. So ln of y, because the C naughts cancel. But the natural log of 2 is a constant number. So just so you can see why this is linear, let's change R to y, and K is a constant, so M, and ln of 2 is another constant, which we will call N. N is equal to ln of 2. So if y is equal to a constant, what type of line is that? Well, that's the equation of I probably shouldn't have used M for K, horizontal line. Sorry about that if that was confusing. wasn't thinking ahead long enough. I just chose m and n because they're right next to each other. M is a constant. M is not equal to 0. So, and it's not the slope. I'm using it to mean something else other than the slope. So it's the equation of a horizontal line. So the answer is yes, linear. So let's look at the second one. The second question posed is the average global temperature increase measured in degrees Fahrenheit is given by the function T of R, so R is our input variable, is equal to 1.03 times R. Right, TR is the function of K. So let's do that. And right here is the main stuff. So since this is a video, and you can go back and read all of this stuff I'm erasing right now, I'm just going to erase it and use this space, decrease. So this is 7b. So we're given T of R, so T is a function of R. In other words, this is like f of x. Our input value is R, is equal to 1.03 times R. Now I'm going to erase that because I want to write up underneath of it. I just did that so you can see what's going to go on. Well, this is equal to 1.03. And what is R equal to? Times K times ln of C over C naught, which is equal to K. I'll put the K not in front, but remember K is a constant. We don't know what it is, but it's some constant. It's not a variable. That's 1.03 K, which is some constant, times the log of C over C naught. And now I have it written as a function of K. So apparently the C and the C naught are given, and they're going to let K vary, so I take it back. They want this to be the input variable, so K varies. So basically, using this function, you can experiment given fixed values of C and C naught. You can experiment with different values of K, and remember the constant K has to be determined experimentally, and it will have some kind of a graph that will be more or less like an exponential graph. I mean, not exponential, but logarithmic. Quickly, something like that. That would be the function T of R. And the input value would be K, and this is T of R. Okay, good enough. Really not that difficult, the problems. Just, again, slowly exploring concepts. So now we're going to do the last thing, and it's the change of base theorem. So if you notice on our calculator, the only thing I have is log to the base 10 and the natural log. What happens if I want to compute the log to the base 5 of 17? There isn't a base 5 logarithm on my calculator. Well, the reason is we don't need one. Because right here we have a formula for the change of base. So the log to the base, so let x, a, and b be positive real numbers where neither a or b are equal to 1, because they're going to be our bases. the following holds. Log to the base a of x. Now you choose any log, any base b you want, it doesn't matter. Any base b. So you choose log to the base 10 or the natural log. It's equal log to the base b of x divided by log to the base b of a. So let's use that formula. I'll actually write it here. Change your base formula. Log to the base a of x is equal to log to the base b of x divided by log to the base b of a. You choose the base b. For this side, you get to choose. So for us in our calculators, that's going to be 10 or e, which we're going to use log or natural log. So we're asked to find the value of log to the base 5 of 17. So for this one, let's use the base 10 log. So that's going to be the base 10 log of 17 divided by the base 10 log of 5. So let's calculate that. So here I'm going to take the log of 17, the log of 17 divided by the log of 5. And I'm going to get 1.76, which I'm checking to make sure that that's the right answer, and indeed it is. The reason I'm checking the last answer is the last fiasco I just had. Let's see if we were going to get the same if I choose the natural log. So by choosing the natural log, I go the natural log of 17. I just do that. The natural log of 17 divided by the natural log of 5. We get to choose the base. It says so right there, right? So I chose the base this time to be e. Do I get the same number? I got the exact same number. So here, the base 2 log is really important. And you expect it's going to be a negative number, right? So log to the base 2 of 0.1 is, I can use log to the base 10, but we did that already. Let's use the natural log. Log of 0.1 divided by the natural log of 2. So let's calculate that. So we're going to do the natural log of 0.1 divided by the natural log of 2. And we're going to get minus 3.32. And that's what I got earlier. Let's use the base 10 choice for a base instead. So I'm going to use log to the base 10 of 0.1 divided by the base 10 log of 2. And I'm going to get minus 3.32, exactly the same as I did before. So know your change your base theorem. And right here, this is going to be mathematical experimentation. So this is going to be, like I said, I've not decided how you're going to get this. It'll either be extra credit, a homework, or it will appear on the Canvas portion of your next exam. Think about it. If it appears on the Canvas portion of your next exam, it's an exam question that you actually get to figure out beforehand. That's kind of nice. So suppose you're studying an ecological system with a total of 1,000 animals. There are 3 different species of animals whose populations are P1, P2, and P3. So those numbers stand for how many of each animal there are. So if your population is lions, tigers, and rhinos, P1 would be how many lions, P2 is how many total tigers, P3 is how many total rhinos. They all have to add up to 1,000. So one measure of how diverse in terms of species the system is can be obtained by the following formula. H is equal to minus, in brackets, a sum of terms. P1 divided by 1,000, that's going to be a number, times the base 2 log of P1 divided by 1,000, plus P2 divided by 1,000 times the base 2 log of P2 divided by 1,000, plus P3 divided by 1,000 times the base 2 log of P3 divided by 1,000. Where H is a measure of diversity, and H is less than or equal to log to the base 2 of 3. So here is your assignment. Experiment with different values of P1, P2, and P3. So this is a calculator assignment. So that the calculated H value is greater than 0.95 but less than 1.05. I don't care where it is in that range, but it has to be in that range. Note that the sum of your populations have to be 1,000. So the easiest way to do this is to come up with 3 numbers, P1, P2, and P3, that total to 1,000. You will have to use the change of base theorem to calculate the base 2 values and plug them in, use a calculator or a computer, and check the H value. If that doesn't get within your right range, experiment with moving populations from one species to another. Take 10 away from P1 and add it to P2. So you're taking it away from one and adding it to the other, so the total population hasn't changed. When you get a feel of the outcome, try experimenting with changing the values of all 3 populations. Check each time that your numerators all add up to 1,000. So this is a calculator or computer-based experiment. I'm expecting almost all of you to use a calculator for this. If you know how to code, I coded this up using Sage. It's basically a Python-based library and interface for mathematicians. But if you know how to code, you can experiment with coding the solution. And if you attempt to code this, you have to add in your code, because I have a feeling your code is going to be going through all these different values of populations. The population P1 values always have to add up to 1,000. So I'll send you out an email about how this will appear. Thinking about it now while I'm talking about it, I'm almost thinking this would be a good exam question for the Canvas portion of exam 3, because you can just have your experimental results there and just have them written down on a piece of paper and take a picture and upload them that way. So that's all for 4.4, and have a good night.